Welcome back to the deep dive. Today, we're peeling back the curtain on MRI. Not just looking at those amazing internal images, but really getting into the engine room. We're talking about the hidden part, the raw data that makes it all happen, case space.
Absolutely. K-space, it's fundamental, but yeah, definitely not something most people ever see or even hear about unless they're, deep in the field.
And we're drawing on some serious material here, physics texts, specific papers on case space formulation, even some really cutting-edge stuff about AI optimizing the whole process.
That's right. We're going from the basics right up to the latest research.
So our mission today is pretty technical. We want to trace that path step by step from a single proton spinning inside you to a data point plotted in this case-space matrix. How does the scanner physically write that data using magnets?
It's all about those magnetic field gradients. That's the key.
Okay, let's unpack this then. What is case space, fundamentally? I saw a quote comparing navigating it to flying an easily maneuverable rocket. That sounds intense. What's the rocket?
Yeah, sequence programmers love that analogy. It really captures the control you have. So simply put, K-space is the raw data matrix. It comes straight off the scanner's receiver coil.
Before any image processing.
Exactly. Before the Fourier transform that gives you the picture you recognize. Think of it as the frequency domain version of the image. The rocket, well, that's the net magnetization vector we create.
Okay.
And the engines steering that rocket. Those are the gradient coils. We use them to push the magnetization around this K-space landscape.
So if I somehow got a printout of case-space data, it wouldn't look like a brain slice or a knee joint.
Not even close.
Exactly.
It's a map of spatial frequencies. Less like a photo, more like a collection of wave patterns. Think of different sets of stripes, horizontal, vertical, diagonal, some close together, some far apart.
And case-space is the recipe for mixing all those stripes.
That's a great way to put it. Each point in K-space tells you the amplitude and phase of one specific stripe pattern needed for the final image. A single point doesn't map to a single pixel. It contributes everywhere.
Okay, interesting. So to understand how we map these frequencies, these stripes, we need to rewind. Back to the absolute basics of MRI physics. Why do we even get a signal?
Right. It all starts with hydrogen nuclei, protons. They're everywhere in the body, water and fat mostly.
And normally they're just spinning randomly.
Randomly oriented, yeah. They're tiny magnetic fields, all pointing in different directions, so overall they cancel out. No net magnetism. Nothing for the scanner to see, basically.
Until we turn on the big magnet, the main field, B0.
Exactly. The B0 field. Huge static field, measured in Tesla. When you put a patient in there, those random protons, well, a tiny fraction more aligned with the field than against it.
Just a tiny majority.
Tiny, but enough. Enough to create a net magnetization vector, M, pointing along the direction of BO. We call that the longitudinal direction, usually the z-axis.
And the plane perpendicular to that is the transverse plane, X and Y.
That's the one. So we have this net magnetization aligned with Z, but it's not just sitting there, it's also precessing.
Wobbling, like
Yeah.
a spinning top.
Precisely like a spinning top in gravity. It wobbles, or precesses, around the B0 field lines at a very specific frequency.
And that frequency is crucial, isn't it? The Larmor frequency.
Absolutely crucial. The Larmor equation tells us that frequency, omega 0, is directly proportional to the magnetic field strength B0. Omega dollars, gamma B dollar is 3.
Yeah.
Gamma is just a constant for hydrogen.
So if B0 is perfectly uniform everywhere,
Then every proton in the entire volume is precessing at the exact same frequency, one single note.
which is useless for imaging because we can't tell where the signal is coming from.
Right, so we have this aligned precessing magnetization, but it's aligned along Z. We can't measure it easily there. We need to knock it over.
That's the excitation step.
That's excitation. We hit the system with a short radio frequency pulse, the B1 pulse, and crucially, it has to be at the Larmor frequency.
Like pushing a swing at just the right moment. Resonance.
Exactly like that. It transfers energy efficiently and tips that net magnetization vector M away from the z-axis and down into the transverse X-plane.
And now we can detect it.
Now we can. As that magnetization rotates in the XY plane, it acts like a rotating magnet, inducing a current in the receiver coils wrapped around the patient. That electrical signal, that oscillation, that's the MR signal we record.
Okay, signal acquired, but then relaxation kicks in immediately.
Right, immediately. The party's over,
Yeah.
and the system wants to get back to its low energy state aligned with B0. Two things happen simultaneously. The magnetization along Z starts to regrow. That's T1, or longitudinal relaxation.
And the signal in the transverse plane?
It starts to decay. The individual proton spins get out of sync with each other, and the net signal in the XY plane cancels out. That's T2, or transverse relaxation.
And the speed of these relaxations is different for different tissues.
That's the magic. Fat relaxes differently than muscle, which relaxes differently than fluid. Those differences in T1 and T2 times are what give us contrast in the final image.
So that signal we just generated, the one rotating in the transverse plane, it's transient. It starts dying the moment we create it.
It does. We're in a race. You have to map K-space, navigate a rocket. Before that, T2 decay, or actually something called T2 star decay, makes the signal vanish into noise.
T2 star. What's the star?
Ah, good question. T2 is the inherent natural dephasing due to random spin-spin interactions within the tissue. T2 star includes that, plus dephasing caused by tiny imperfections or variations in the main B0 magnetic field itself. It's always faster, meaning the signal disappears even quicker in reality.
So the clock is ticking even faster than we thought. Milliseconds, maybe?
We're talking tens to hundreds of milliseconds, typically, to get the useful signal. That's the window we have to work with.
Okay, so uniform field, uniform frequency, no spatial information. We need to break that uniformity. Enter the gradient.
Enter the gradients. These are weaker supplementary magnetic fields produced by separate coils. Critically, they can be switched on and off rapidly, and they create a linear variation in the magnetic field strengths across the patient.
So they add a slope to the main B0 field.
Exactly. Imagine the main B0 field is a flat, level surface. A gradient coil, say GX, adds a slight controlled tilt along the X direction. Now, the total magnetic field strength isn't uniform anymore. It linearly increases as you move along X.
And because frequency depends on field strength.
Protons at different X positions now precess at slightly different Larmor frequencies. We've just encoded spatial position X into frequency.
That's the core principle of spatial encoding, and this relates directly to how we move in K-space.
Directly. The position we reach in K-space, let's call it K, is the time integral of the applied gradient waveform G times that gamma constant. So K caret gamma in G.
Whoa, okay, so G, the gradient, is like the velocity of our rocket in K-space.
Precisely. And integrating that velocity over time gives you the position, K, you've reached in K-space. The longer or stronger you turn on a gradient, the further out from the center of K-space you travel in that direction.
This puts the MRI sequence programmer in the driver's seat. They design the GT waveforms to steer the rocket along a specific path.
Complete control over the trajectory. Now, how do we use this for 2D or 3D imaging? We typically use gradients along different axes for different encoding roles. Let's talk about phase encoding first, usually assigned to the high gradient Greek.
Phase encoding? How does a phase difference tell us about Y position? It's not frequency.
Right. It's clever. After the initial RF excitation pulse tips the magnetization down, we turn on the Geek gradient for just a very short, precise amount of time.
A quick pulse of gradient.
A quick pulse. During that pulse, spins at different A locations experience different field strengths, so they precess at different speeds temporarily. Spins higher up speed up a bit, spins lower down slow down a bit relative to the center.
So they get out of sync, phase-wise, like runners starting together but taking slightly different speed bursts.
Perfect analogy. They accumulate a phase difference that's directly proportional to their eye position. Then, and this is key, we turn the Geek gradient off.
The Geek gradient off.
Now, all the spins go back to precessing at the same base Larmor frequency, assuming no other gradients are on. But the phase difference we just created, it's locked in. It persists.
Ah, like a memory. They remember their A position through the relative phase angle.
Exactly. It's a phase memory. The receiver coil collects the signal from all A locations simultaneously, a complex signal containing all these different phases mixed together. The Fourier transform later unscrambles this phase information to reconstruct the E dimension.
Okay, phase encoding encodes one dimension using a temporary gradient pulse and phase memory. How does frequency encoding differ? That's usually GX, right?
It's usually GX, yes. And it's fundamentally different in when it's applied. The frequency encoding gradient, GX, is turned on during the actual signal readout while we're listening to the echo.
Not before, like the phase gradient.
Correct. So while we are actively acquiring the data, the GX gradient creates that continuous linear variation in field strength along the x-axis.
Meaning spins at one end of X are constantly precessing faster than spins at the other end during the measurement.
Precisely. The signal we record is therefore a mixture of different frequencies, where each frequency corresponds directly to an X position. It's not about phase memory. It's about creating distinguishable frequencies during readout.
And again, the Fourier transform is the mathematical tool that decomposes that complex signal into its individual frequency components, mapping them to the T-X axis of K-space.
You got it. So the phase encoding step, determines which line of K-space we're on in the K direction, and the frequency encoding gradient, Gx, lets us sample the data along that line in the Tx direction.
Let's make K-space coordinates, Kx, a bit more concrete. You called them spatial frequencies. High at K means sharp details.
Think of it physically. Kx represents how rapidly the image pattern changes along the x direction. A high x value corresponds to a pattern with many cycles, like fine vertical strikes packed closely together. Low Tx means slow change, like very wide stripes or smooth areas.
And chi is the same for the y direction.
Same for y. So a point way out at the edge of K-space, with high Kx and high K, represents fine diagonal details or sharp corners. A point near the center, Kx0, K0, K0, represents the overall average brightness or the slowest possible variation across the image, basically, DC, offset, and contrast.
So high K, fine detail, low K equals broad contrast. That's a critical takeaway.
Absolutely fundamental for understanding image quality and artifacts. The final image emerges when we sum up all these spatial frequency components we've measured, weighted by their values in K-space, using that inverse Fourier transform.
Okay, we know how gradients write the data. Let's look at the K-space map itself. The sources mention reframing how we think about the signal not as a complex function of time, but as sampling points on a static map. QK, why is that shift helpful?
It's hugely helpful for designing sequences. Instead of thinking about the complicated, time-varying signal ST coming out of the receiver, we can think about a fixed underlying landscape, QK, in K-space. Our job as sequence designers is simply to fly our rocket along a path, KK, and take snapshots, sample the value of QK at various points along that path. The signal we measure is simply the value of QK at the location KK.
So the challenge becomes choosing the most efficient path, KT, to map out the important features of QK.
Exactly. And since we always start acquiring data right after the RF excitation pulse, before we've applied much gradient integral,
the path KT always starts at KG, the center of K-space.
Always starts at the origin. KK00, we launch from the center every single time. Where we go from there is entirely determined by the gradient waveforms G2 we choose to play out.
And once we've collected enough samples of QK across K-space,
we feed that grid of data points into the inverse Fourier transform, and out pops the anatomical image, IXY.
This brings us back to why the center of K-space is so dominant for image contrast. Why there?
Because the center, K0, represents zero spatial frequency. It corresponds to the overall signal intensity, the average brightness. Physically, this point in K-space is typically acquired at the peak of the signal echo, the echo time, or TE.
Ah, TE, the time between the excitation pulse and the signal peak?
Right. And how bright that signal peak is depends heavily on how much T2, or T2 decay, has happened during that time TE. If TE is long, the signal at K0 will be weak, giving you a dark T2-weighted image, emphasizing fluids.
And if TE is short?
Short TE means less decay, so the signal at K0 is strong. This gives you brighter images weighted more by T1 or just the proton density itself. So the timing of when you acquire the center of K-space essentially sets the contrast flavor of the entire image.
The center gives the contrast, the overall shape, and the edges, the high K values.
The edges give the sharpness, the resolution, fine lines, borders between tissues, textures that's all encoded in the high spatial frequencies out at the periphery of K-space. The further out you sample, the higher the maximum K value, K max, the finer the detail you can resolve in the final image.
So if you don't fly your rocket far enough from the center,
you get a blurry image. You've missed the high-frequency information needed for sharp edges.
This connects to that fascinating analogy about K-space being like a hologram. Why can a small piece of K-space still reconstruct a recognizable, albeit degraded version of the whole image?
Because of the nature of the Fourier transform. Information isn't localized in K-space the way it is in image space. Every point in K-space contributes, to some degree, to every pixel in the final image. If you chop off the outer edges of K-space, discard the high frequencies, you lose resolution everywhere. The image gets blurry, but you still see the whole object, because you kept the low-frequency data from the center, which defines the basic form and contrast.
Whereas if you chopped off half the pixels in a normal image file, half the picture would just be gone.
Exactly. Missing K-space data tends to degrade the quality of the whole image, rather than erasing a specific part of it.
Okay, now let's tackle that signal decay head-on. The fact that QK isn't truly static because the signal strength is dropping exponentially over time by that factor XP R2T. How do we fight that? Let's compare the two main echo techniques, gradient echo and spin echo.
Right. That decay rate R2 is dominated by those local field inhomogeneities we mentioned, plus the true tissue T2. Signal disappears quickly. A gradient echo sequence tries to recover some signal by reversing the gradient polarity.
So you fly out in K-space using a positive gradient, then you switch to a negative gradient to fly back towards the center.
Yep, the negative gradient reverses the phase shifts caused by the positive gradient, causing the spins to rephase and form an echo signal peak when you get back near the center. It's like rewinding the effect of the applied gradient.
The key limitation is
It cannot reverse the dephasing caused by the static background field inhomogeneities. Those effects are still there, relentlessly causing signal loss. So the signal decay in a gradient echo sequence is always governed by the faster T2 rate. You lose signal faster, especially in areas with poor magnetic field uniformity, like near sinuses or metal implants.
okay, so gradient echo is fast but sensitive to T2 losses. How does spin echo sequence use that 180-degree RF pulse to overcome this?
The 180 pulse is ingenious. Let's say after the initial 90-degree excitation pulse, spins start fanning out in phase due to both T2 and T2 effects. Some are getting ahead, some falling behind. At a time tau later, we hit them with a second RF pulse, a 180-degree pulse.
What does that do physically?
It flips the spin's phase positions. Imagine runners on a circular track. The 180 pulse instantly makes the fastest runners, who were furthest ahead, now the furthest behind, and the slowest runners, who were lagging, now ahead. It reverses their relative order.
So the fast ones now have to catch up to the slow ones.
Exactly. And because the same background field inhomogeneity is still acting on them, the ones that were fast are still trying to run fast but are now behind, and the slow ones are still slow but are now ahead. They all converge. At a time 2 tau, twice the time between the 90 and 180 pulses, they all come back perfectly in phase, creating a strong spin echo signal.
And because this process reversed the effects of the static field inhomogeneities.
The signal decay for a spin echo sequence is governed primarily by the true intrinsic tissue T2 relaxation time, not the much faster T2. We've effectively canceled out the machine and location-dependent dephasing.
Which means the contrast we see is much more dependent on the actual tissue properties, which is great for clinical diagnosis.
Hugely valuable. It lets us isolate and see differences based on T2 values, which vary significantly between healthy and diseased tissues.
All right. Physics-defined, decay mechanisms understood. Now, the strategies. How do we actually chart K-space? You mentioned hundreds of ways to control the gradients, GOT, to trace that path KT.
Yeah, it's a whole field of engineering pulse sequence design. Broadly, we can think about multi-shot versus single-shot techniques.
Multi-shot being the traditional way.
Traditional way. Like standard Fourier transform imaging, often called spin warp, you do one RF excitation, apply a specific phase encode ingredient, say for keyline #1, frequency encode, and read out the keybox data for that line, wait a bit, ETR. Then repeat with a different phase encoding gradient for keyline #2 and so on. You need as many shots or excitations as you have lines in the K direction.
Which could be 128, 256, 512 shots. Takes time.
Takes time. Seconds to minutes. And the alternative.
Single shot, like echoplanar imaging, EPI.
EPI is the classic example. After a single RF excitation, you use rapidly switching gradients to just zip back and forth, covering the entire K-space grid, or a large chunk of it, in one go within tens of milliseconds.
Wow. So incredibly fast. Essential for things like fMRI, watching brain activity in real time, or imaging things that move a lot.
Absolutely. Speed is its superpower. But it often comes with trade-offs in image quality or artifact sensitivity.
Let's look at 3 key trajectory patterns mentioned. Cartesian, radial, and spiral. Cartesian first, the rectangular grid.
The workhorse. You move out along make, you jump up one line and bakes, move back along nakix, jump up again, filling a nice, neat grid. Computationally, it's beautiful because the fast Fourier transform algorithm is tailor-made for reconstructing data on a Cartesian grid. Very efficient.
But you mentioned it's sensitive to motion artifacts. Ghosting.
Highly sensitive.
Yeah.
Because if you're filling a 256 by 256 grid line by line over, say, 2 minutes, and the patient breathes or swallows or twitches between line 100 and line 101...
the data becomes inconsistent.
Exactly. That inconsistency manifests as ghost images, repetitions of moving structures smeared across the image, usually in the phase encoding direction.
Okay. How does radial sampling help with motion? That's like spokes on a wheel, right?
Right. You shoot out from the center along one angle, then do another shot straight out along a different angle, and repeat many times. Think spokes radiating from the hub.
What's the advantage?
The big advantage is that every single shot passes through the center of K-space, K0. Remember, the center holds the main signal intensity and contrast information. By repeatedly sampling it, even if there's motion, the contrast information remains relatively consistent.
So motion doesn't create those sharp ghosts?
Less so. Motion tends to cause a streak-like blurring radiating from the moving object, which is often less disruptive than distinct ghosts. It's inherently more motion robust. The downside,
Always a downside.
the sampling density is very high at the center but gets sparse further out. This can lead to some blurring or streaking artifacts, especially at the edges, and requires more complex reconstruction algorithms than simple FFT. Resolution might not be quite as good as Cartesian in a perfectly still patient.
Got it. And the third one, spiral imaging.
Spiral is cool. After one excitation, you use smoothly varying G-grade gradients to trace a continuous spiral path outwards from the center of K-space.
Covering low and high frequencies relatively quickly in one shot.
Exactly. It's often a single-shot technique, making it very fast. And because it covers the periphery well, it can achieve good resolution efficiently.
The sources highlighted a hardware benefit too, easier on the gradients.
That's a key practical advantage. To draw a smooth spiral, the gradient amplitudes change relatively slowly and continuously. Compare that to Cartesian EPI, which needs really sharp, rapid switching of the frequency encoding gradient as it zips back and forth.
Those rapid switches are hard on the hardware.
Very hard. They demand high slew rates, generate more heat, cause more acoustic noise, and can even stimulate peripheral nerves in the patient. The smooth changes in spiral are much gentler, allowing potentially faster acquisition within the hardware's comfort zone.
Interesting engineering trade-off. Now let's revisit that signal decay, XPR2T. What happens if the sequence designer just ignores it when planning the trajectory?
Well, you can't really ignore it. It happens. But if you don't account for it in the reconstruction, artifacts appear. One effect is called apatization, or blurring.
How does decay cause blurring?
Remember, higher resolution comes from the outer parts of K-space. These are typically acquired later in the sequence, especially in trajectories like EPI or spiral. By the time you get out there, the signal has decayed significantly.
So the high-frequency data points are weaker than they should be.
Exactly. It's like you've applied a filter that dampens the high frequencies. Mathematically, the decay function acts like a weighting function, multiplying the K-space data. When you reconstruct, this suppression of high frequencies results in a loss of sharp edges, a blurry image.
And if the K-space trajectory is asymmetric in time, like maybe you collect the top half much later than the bottom half?
Then the decay affects the two halves differently, creating asymmetry in the data that leads to specific artifacts, often ghosting or smearing, particularly in multi-shot sequences.
Can we try to fix this decay problem computationally? You mentioned numeric correction.
Yes, if you know or can estimate the decay rate R2, and you carefully record the exact time t when each K-space data point was acquired.
You can mathematically boost the signal back up.
You can try. You multiply the measured decayed signal value by the inverse of the decay factor, by x plus R2t, to estimate what the signal would have been without decay.
Sounds powerful. How much does it help?
It can effectively extend the useful acquisition window, allowing you to collect data for longer or use faster sequences that would otherwise suffer too much decay. It can mean significantly shorter scan times in practice, maybe reducing a scan from 5 minutes to 30 seconds in some cases.
But there must be a catch.
Big catch. Noise. The correction factor xput plus R2t grows exponentially with time. While you're boosting the decayed signal, you are also boosting the random noise that was acquired along with it by the same exponential factor.
So the points collected latest get amplified the most, noise and all.
Precisely. Push it too far, and the noise just swamps the corrected signal. You hit a wall where the amplified noise dominates the image. It's a balancing act.
Okay, so we're constantly fighting physical limits. Gradient strength, how hard can we push? Slew rate, how fast can we turn? And signal decay, how long does the signal last? This brings us to the really cutting-edge stuff. Using AI, specifically deep learning, to optimize the K-space trajectory itself.
Exactly. We've sort of hit diminishing returns trying to build ever stronger, faster gradient hardware. It gets incredibly expensive and complex. Plus, faster sampling always means wider bandwidth, which inherently increases noise SNR drops.
So the idea is, instead of just building a faster engine, let's find a smarter route for the rocket.
That's the essence of it. Instead of relying on predefined human design paths like Cartesian or spiral, what if we could learn the optimal K-space trajectory for a specific imaging task, given the specific hardware constraints?
And this is where neural ordinary differential equations, or neural ODEs, come in.
That's one promising framework, yeah. You model the K-space trajectory, K-toy, as the solution to a differential equation, where the dynamics, how X changes over time, are parameterized by a neural network.
So the neural network learns the best way to steer KT.
It learns the optimal gradient waveforms GT that generate the best KT. You typically initialize it with a standard trajectory like a radial or spiral path, and the network learns to deform and adjust that path to maximize the information captured within the allowed scan time, respecting the hardware limits.
And those constraints are critical, right? The maximum gradient strength, Gmax, and maximum slew rate, SMAX.
Absolutely crucial. Gmax is the top speed of the rocket. SMAX is how quickly it can accelerate or change direction. Essentially, it's agility. You must bake these physical limits into the optimization process.
Why is SMAX often the bigger bottleneck?
Because making sharp turns or rapidly reversing direction requires huge instantaneous changes in the gradient currents. That's what demands high slew rates. If you let the AI optimize without considering SMAX, it might design trajectories with physically impossible, infinitely sharp corners.
Which the hardware simply can't execute.
Right. So the neural ODE has to learn to generate smooth, hardware-friendly trajectories that stay within the Gmax and SMAX limits of the specific scanner it's being trained for.
So the AI learns a path tailored not just to the anatomy, but to the actual physical machine.
That's the goal. And the most advanced approaches use joint optimization, meaning they don't just train the neural ODE to plan the trajectory. They simultaneously train another deep learning network, usually a convolutional neural network, CNN, to perform the image reconstruction from the data collected using that trajectory.
So the trajectory planner and the image reconstructor learn together.
Yes,
Okay.
they co-adapt. The trajectory network learns to sample K-space in potentially weird, non-uniform ways that are information-rich, and the reconstruction network learns how to best turn that specific sampling pattern into a high-quality image. It's a synergistic process.
And does it actually work? Do these learned trajectories outperform the standard ones?
The published results are really impressive. When you compare images reconstructed from data acquired using learned, physics-constrained trajectories versus standard Cartesian, radial, or spiral paths, especially when pushing for faster scans, high acceleration factors, the learned ones often show significantly better image quality.
Better metrics like PSNR and SSIM, fewer artifacts.
Yes, typically higher quantitative scores and visually fewer artifacts like blurring or aliasing. The AI learns to allocate the limited sampling time extremely efficiently, focusing on the most critical K-space regions needed to avoid those artifacts.
And it even adapts the trajectory based on what's being imaged, the context awareness.
That's also very cool. If you train the system on brain scans, which tend to have smooth tissues and thus most K-space energy concentrated near the center, the learned trajectory reflects that it samples the center very densely.
But for something with more edges, like a knee,
For knee images, full of sharp bone cartilage tendon boundaries, you need good, high-frequency information. The network learns this and designs trajectories that spend more time sampling the outer regions of K-space to capture that detail. It adapts its strategy based on the expected K-space distribution of the target anatomy.
incredible. So wrapping this up, we've gone from protons aligning in a magnetic field to using RF pulses to create a signal, and then crucially, using carefully controlled magnetic field gradients to encode spatial location into that signal's phase and frequency.
Which allows us to map out K-space, this spatial frequency domain representation of the object.
We explored different mapping strategies, Cartesian, radial, spiral, each with pros and cons related to speed, resolution, and artifacts, all fundamentally constrained by that relentless T2 signal decay.
And the core insight really is that MRI acquisition is this incredibly sophisticated dance against time, trying to paint a detailed picture of this rapidly fading frequency landscape, QK, using gradient fields as our brushstrokes.
So what does this all mean moving forward? It feels like the future isn't just about bigger magnets, but smarter software.
I think that's exactly right. Computational intelligence, like these neural ODE frameworks, offers a path to push performance beyond what hardware improvements alone can easily deliver. By optimizing the data acquisition strategy itself, tailored to the hardware and the specific clinical question, we can get faster scans and better images.
We're moving away from relying solely on those fixed, decades-old patterns like Cartesian grids.
Towards dynamically generated, context-aware, physics-constrained optimal trajectories. The machine learning system designs the best way to fly the rocket for this patient, this body part, this scanner, right now.
Which leads to a final, kind of provocative thought. As these AI-designed trajectories become more complex and maybe less intuitively understandable to human engineers, will we reach a point where we trust the AI pilot completely, even who don't fully grasp why its chosen path is the most efficient? We just know it delivers the best image faster. How far can that optimization go?